Good evening to all and all. I will start our today's session. So last class we finished our discussion based on our extended Euclidean algorithm, right? Today we move on to the next part called modular arithmetic. So which forms one of the most important mathematical part of cryptography, that is modular operation. So till now we just saw everything based on division rules also, right? That is, if you have any two integers like a and n, and if you both are going to be dividing each other, then it will be getting quotient and remainder. Okay. So in modular arithmetic, we are going to take only one output among these two, that is from quotient and remainder. I am going to concentrate only on the remainder part. Okay. So in this we are going to discuss the following topics. So what do you mean by modular operator? What do you mean by set of residues? What does a congruence operation means? And then you come across a new set called Z suffix n. Then your addition and multiplication table, and what are different types of sets which can be formed using this modular arithmetic. To start off with, okay, the modular operator is generally denoted as mod, and the input n which is going to be present after this mod operator is called modulus, and here the output will be called as a residue, not a remainder. We used to call them as a residue. So this diagram shows the difference between a division algorithm and a modulo operator. So if you take a division algorithm, it is going to take an element called a from a set of integers which ranges from minus infinity to plus infinity, right? And we are going to give a n which is a positive value. Okay, so if a is going to be divided by n, it will be giving me a quotient and the remainder, and we are concentrating that the remainder should be a non-negative value, right? Whereas in this case of modulo operations, we will be writing a mod n, okay, and the output will be only remainder. Here the quotient will be dropped in the modulo operation. Right. So these are a few examples. So if you take 27 mod 5, okay, if you divide 27 by 5, I'll be getting a result of remainder as 2, or to be specific, we used to call them as a residue as 2. Then 36 by 12 is perfectly divisible, so my R is 0. As if you divide minus 18 by 14, I'll be getting minus 4. If you want to convert them into a non-negative value, add the value of n to it. So minus 4 plus 14 gives me R is equal to 10. Similarly, in this case, R is equal to 3 when you divide minus 7 by 10. So in this case, or divide and sense, we are performing modulo operations here, right? So I hope everyone are clear with the modulo operator. Right? Anyone have any doubt in this modulo operation, you can ask me. If you're okay, so I'm clear with the modulo operations, how it works, that is converting a negative value into a non-negative values. If you're clear, can you raise a hand? Yes, I think only guy is responding. What about others? Now we move on to our next terminology called set of residues. So till now we just saw a variable or a set called z, right, which denotes a set of integers. Now I'm going to create a subset called, okay, z suffix n, okay, which is called as a set of residues or set of least residues of a modulo operator n. That is, these elements, if I say z suffix n, it will have elements starting from 0. So there will be a no negative value here, starting from 0 to n minus 1. So if I say z suffix 2, it is 0, 1, 6 means 0, 1, 2, 3, 4, 5, 11 means from 0 to 10. So from this you can also able to infer, if I say z suffix 6, okay, if you take any integer and if you perform modulo sets, you'll be getting answers as either 0, 1, 2, 3, 4 and 5, not apart from this. Am I right? Whatever the value of a you take, it can be from a set of integers from minus infinity to plus infinity, and if it perform a modulo operation of 6, I'll be getting answers from 0 to 5 now. Yes or no? People who are accepting with this, can you raise hands? whatever the value of A you're going to take, and I'm taking modulo operation sets, whatever the value size. If you simply take mod sets, I'll be ending up with answers from 0 to 5 alone. Yes or no? Right. So here you can able to see, I can able to call the set of residues as a numbers from 0 to n minus 1, or I can also able to say that a set of residues are nothing but the possible outcomes of any modulo operation n. So what are the outcomes from a, if you take a modulo operation with respect to n, can be found as element inside a particular set. Right. So now we
So
move on
here,
to,
when
yes,
you
yes.
wrote A mod 6, that's like the general for Z6 or Z2 or anything, right?
Yes,
For
if
any of those sets.
yes, for any other sets, if I take 11, whatever the value of A you take, and if you take a modulo of 11, you'll be getting answers from 0 to 10 alone, not apart from that, whatever the value of A may be.
So can
So
we have
this,
a mod of the entire set? Like that also would give a different set for it.
I mean, I can't able to get your point. I mean, this A
So,
will be taking the values from set of integers.
so we can have one set of A's, right?
Yes, yes. I mean, what you're asking in a sense, if I simply,
So
can I?
what I asked was rather than taking each element, we can have a modulo of the entire set.
Yes, if
Can we
taking
have?
entire set Z mod 11 or 6 means either you'll be, I mean, in this case, if you take the entire set of set and take modulo operator of 11, you'll be getting answers from 0 to 10 alone. This is what you're saying, right?
Yes, sir.
Yeah, we can also call this way also.
Okay, sir.
Anyone have any other doubts, guys? Like, or if you have any way we can able to call them, you are most welcome. Thank you. I think, is it Arun who spoke now?
Yes, sir.
Okay, okay. Is anyone have any other suggestions or anything from your side? Then I'll proceed. Yeah. Next, we come to an important operator in modular arithmetic or modular arithmetic called congruence operator. So this congruence operator will be denoted using the three lines like similar to an equal sign. Okay, this congruence operator will denote a relationship between two integers under a particular modulo operation. So here you can able to see they are saying that 2 and 12 are congruent to each other under a modulo 10. 3 and 23, 13 and 23 are congruent under a modulo 10. 3 and 8 are congruent under modulo 5. Can anyone able to infer what this this operator does? To be in a layman's language, if you want to replace this congruence operation with the equal sign, I can able to write this expression as 2 mod 10 will be equal to 12 mod 10, which means this is also giving going to get me as answer as 2. This is also going to get answer as 2. If we take this one, which denotes 13 mod 10 will be equal to 23 mod 10. That is, here answer is 3, answer is 3. That is, I can able to call two numbers are congruent to each other under a particular modulo operation, so that they are going to give same residue values. It means then I can able to call these two elements, that is 13 and 23 in this case, are congruent to each other. I hope you people are clear with congruence operator. Am I clear, guys, regarding
Yes.
congruence operation? Yeah. So you can take any elements from a set of integers. So in this diagram, you can able to see we are taking these values of -8, 2, 12, and 22, and they're performing a modulo 10. And you can able to see all the resultant will be belonging to this particular set of residues Z10, as well as you can able to see the numbers -8, 2, 12, 22 all are congruent to each other because they're going to give me a residue of 2 under modulo 10. So this is how the congruence relationship is used. right? Now we move on to our next topic called what are the operations which can be performed in the set of residues, that is Zn. So till now we just took a discussion on binary operations over the set of integers. Now we are going to define the same binary operations towards the set of residues, right? So here also we are going to perform three binary operations like addition, subtraction, multiplication, and after that we'll be performing a modulo operation with the modulus value of n, and here the output will also be an element of z suffix n, right? So here you can able to see perform the following operations. The inputs are going to come from the particular z suffix n. Okay. So here 7 plus 14. I want you people to solve this one and post the answer in the chat box. They are asking 7 to 14 under z suffix 15 means you have to take modulo 15, and here subtract 11 from 7 under your set of residues of 13. Here I want a non-negative value. Okay. And they are asking to multiply 11 by 7 under the set of residues of 20. So can you people post the answers for these three in the chat box separated by commas? I want one more answer extra. Only Arun is interacting with you. So as I said, Arun is alone interacting with me. I want one more answer. Arun, his answers are correct. Can you check 6, 6, 11?
So by adding 10, it will be for the negative one, it will be 6, right?
No,
So did you
you
say is it correct or are you asking?
I'm asking to verify. This is 13, not 10.
Oh,
Here it
okay.
is 13, here it is 15, here it is 20. That's why I just asked you to verify. You made everything okay, but you made a mistake with the model operation. All the three has different model operators. Guys, I want response from other guys also. Or you people are there in the class or not? It's 911, okay.
So but for negative, you said we'll add 10 only. That so that 10
No,
depends on the modulo.
yeah, we won't add 10 as a fixed value.
Okay.
Whatever the modular value here, you'll be adding.
Okay,
That's the
sir.
thing. So here you'll be getting minus 4, right? You'll be adding 13 to
Okay.
it, then only you'll be getting answer.
Okay, sir.
Right, you'll be getting plus 9. So here you'll be getting 6, 9, and last one is 17.
Oh, okay, sir. I made a
Eh,
small.
yeah, this one is 20. Right, so last one is 17 here. Right, these are basic operations, and based on this there are three properties which can be applied, or simply we can able to say there's a one property with different binary operation. The first property is nothing but if you take a mod n, yeah, the a can be any integer from z, okay, which is going to be added with the b mod n, and the entire operation is undergoing another modulo operation with n. It will be giving the same answer as a plus b mod n. You can able to see the example here. I'm taking 11 mod 8, so 11 mod 8 I'll be getting 3 plus 15 mod 8 I'll be getting answer as 7, okay, which will be something but again because the entire thing is again going for modulo with 8, right? Mod 8 gives me 10 mod 8, which is again 2, and here you can directly go with a plus b directly. 11 plus 15 will be 26. 26 mod 8 will also give the same answer as 2. This is the basic identity of binary operations in set of residues. Like this, we can also apply it for subtraction as well as for multiplication rules. Right. So, and this diagram shows the difference between the original process where you'll be performing the binary operations. Then you go for the modulo. You can also, if you want to make the binary operation more simple, suppose if your A and B are very large numbers, you can take the modulo for each and every element separately. Then you can perform your binary operation. And again, if your number exceeds the value of n, you can go with the modulo. Then you'll be finding that all the elements which are coming out of this operation will be an element which belonging to the set of residues that suffix n. Right? Guys, are you people clear with this modulo operations on ZL? If it is clear, raise a hand. If you have any doubts, kindly ask me. Okay, I think in today's class, I'm going to give attendance one and only one person alone, I think so. Who is responding? Like this is an example of the above properties. Such large numbers, you can go with the properties directly by taking modulo. Then you can go with the binary operations there. Right. And here also we can able to use a certain identity of a third property, that is using multiplication. That is, if you find any modulo operation in this format, that is any value which is in power of 10 power some n mod x can be written as 10 mod x the whole power n. That is the only condition is nothing but the value should be, the value of a should be in form of 10 power something. That is 10 power some n value. Right. For example, if you take 10 mod 3, the answer is 1. If you have any 10 power even 100 mod 3, it's nothing but the value which you're going to get 10 mod 3 is 1 whole power 100. You will be getting 1. If you take the last one, 10 mod 7 is 3. Same thing, if you have a 10 power 100 or 10 power 10, as of now, just assume 10 power 10 mod 7, there's nothing but 3 power 10 mod 7. Right. So you'll be 3 power 10 mod 7. Then you can solve it. So this is an identity based upon the third property of a binary operations over the set of residues z suffix n. Right. Now we move on to the most important topic with respect to modular arithmetic is concerned. That is to find the inverse of any particular operation. Right. If you remember properly in our module on discussion, for additive ciphers, we will be using the inverse of this addition value called additive inverse in our decryption part. And for multiplication, we used the inverse called multiplicative inverse. Okay. So I want everyone to listen to this carefully because you will be using this method to find the respective inverses. Okay, which will be used in the decryption part. Okay, already people had an idea about how to have the additive inverse. Simply put the negative sign for the particular number. But you people haven't learned how to compute the multiplicative inverse. So we start off with finding the additive inverse. For example, if you have two numbers A and B, okay, which belong to the set Z suffix n. Okay, both A and B are the elements from Z suffix n, and I'm going to call the A and B are additive inverses of each other. That is, A will be the additive inverse of B and B will be additive inverse of A. I'm saying both are additive inverse to each other. When I can able to call them as inverses, additive inverse to each other means if they satisfy this expression. That is, if we add this A plus B, it should be congruent to modulo n. Or I can able to say, if I simply go with A plus B mod n, it should be equal to 0 mod n. What is the value of 0 mod n? Can anyone tell? If we take 0 and if we take a mod with 0, what will be the answer? I'm having an integer a as 0 and if take mod my modulus of 0, so with whatever the value of n maybe, assume the n is a positive value. What will be the output?
0.
Yeah, 0. Okay. So we can able to simplify this expression. How, in the sense I can able to write it as a plus b mod n equal to 0 mod n, or simply I can able to conclude this as a plus b mod n should give me answer to be 0. If both are additive inverse to each other, we will be getting this output. Okay, we'll see an example. Here they are asking you to find all the additive inverse pairs in set of residues under Z suffix 10. So before going into this, can anyone tell or post in the chat box what are the elements present in Z suffix 10? From that only I can able to proceed. First you should know what are the elements present in Z suffix 10, and for each element I am going to find the uh, additive inverses. You can post the answer in the chat box. Yes, Arun, you are correct. 0 to 9. Right. So I'll be having elements from 0 to 9. Now I have to find the additive inverse of each and every element in this set. Right. First I'm taking the first element 0. I have to find the additive inverse. Assume this is an inverse value, you have to find such that if you take modulo with 10, here in this case the value of n is 10, it should come to 0. So what will be the value of this inverse? What are the, I mean, these values which are going to put, it should be elements from this set alone. What can be substituted here such that this expression holds good? 0 plus that particular element will, under modulo 10, will give me 0. Can people tell? So that that element will be a inverse of 0. The only condition is nothing but the element which are going to put as inverse should be from the set of residual sets of its 10. Okay, so the 0 plus that particular element will
So
give
0.
me, yeah. So for 0, okay, the additive inverse is itself. So 0 mod 10. So for 1, next element, 1 plus that particular element of inverse which you're going to find, mod 10 should go for 0. What is this element? It can be
9.
9, right? Or simply what we can do, since generally what we used to write as additive inverse, in the sense we'll put minus sign to the particular element. Minus 1 mod 10 is the additive inverse of 1, means if we convert this minus 1 into a non-negative value, which is nothing but minus 1 plus 10, which is nothing but 9. So for 1, the additive inverse is 9. Like this, if we go with other elements like 2, 3, 4, 5, 6, 7, 8 and 9. Can you people post the pair? For first pair is 0, 0, second pair is 1, 9. Can you people post the answers for 2, 3, 4, and so on in the chat box? That is the respective additive inverses. 2, 8, 3, 7. Yes, Arun. Yep. 4, 6. Last one. Yeah. 5, 5. Right. Totally we'll have 6 pairs. Because then after 5 you go for 6. It's inverse to each other, right? For 6, 7, 8 and 9. So these are the additive inverses. Additive inverses are very easy to find. Okay. So you can able to say all the elements which are present in a set of residues called sets of its 10, okay, have their additive inverse within the particular set itself. Right. I hope you are clear with additive inverse. If you are clear with additive inverse, can you raise your hand? Thank you, Usha. Second candidate to respond. Happy at least. Right. Now we move on to the important topic, that is multiplicative inverse. Again, if you take two integers a and b, okay, and I can call them as multiplicative inverse to each other under a set of residues of Zn if it satisfies this condition. So if you see the additive inverse condition, if you add this two and if you take modulo n, it should run for 0. Whereas here, simply speaking, if you multiply these two elements and if you take a modulo n, okay, I should get, this is actually mod n, I should get the answer as 1. That's the only condition. So I have to choose the values of, if you take A, you have to choose the value of B in such a way that if you multiply these two, I should get the output as 1. Now let's see. Now asking the same set, find all the multiplicative inverses in Z10. As we already know, the elements present in Z10 are 0, 1, 2, up to 9. Now I'll take the first element 0. I have to find the multiplicative inverse of 0 such that if you multiply this 2 and if we take mod 10, I should get the answer as 1. What will be the value? And again I'm saying the value which you're going to put here should be belonging to this particular set alone. What will be the answer? Any guess? Smaller numbers we can go with the guesses, but for larger numbers where you need to find the multiplicative inverse, there is a separate method or a theorem to find it. As of now, just go with trial and error method. Can you people give a guess?
So does the multiplicative inverses have to be in Z10?
Yes, yes. Can you able to find the answer for this? Because if you multiply whatever the value here, you
So
put,
it all be 1.
it will end up with 0.
0 and 1.
We can't able to, no, if you even if you put 1 here, 1 second.
So if we have 2, then 2 raised to the power minus 1 is 1 by 2. 2 into 1 by 2 will be 1.
No. Actually, what I just put is nothing but is multiplicative inverse. That is, you have to find the multiplicative inverse. I didn't mean by 0 inverse means 1 by 0. So you have to put an element from this one. No fraction, nothing. That is, if you substitute 1, you substitute 2, 3, 4, 5, 6, 7, 8, 9. Whatever the value you put here, I'll be easy. Anything multiplied with 0, I'll be ending with 0. 0 mod 10, I'll be getting only 0. So we can able to say that we don't have a multiplicative inverse for the element 0 here. Now I'm going for the second element here. And one more thing, not all the elements in a set of residues will have the additive inverse. Okay, it is not mandatory like how we have, how we have in additive inverse, all the elements will have their respective inverses. If you take multiplicative inverse, it is not mandatory that all the elements should have a multiplicative inverse. For example, 0 doesn't have a multiplicative inverse, whatever the value of n may be. Because if you multiply anything with 0, I'm obviously going to end up with the 0 as output, which is not going to satisfy this expression. Right. Now, if you take the second element 1, the multiplicative inverse of 1 is 1 itself. If you take 1 into 1 mod 10, I'll be ending up with 1. So, I have the solution as 1 has the multiplicative inverse as this one. So, can you people tell me the answer for 2? First, tell me whether we have the multiplicative inverse for 2 or not. Then you tell me the answer whether we 2 has multiplicative inverse with respect to Z10. Yes or no? Yeah, Usha said 2, 8, 3, 7, 4, 6, and 5, 5. Okay. Usha, you mean okay. Now you are answering. Okay. That one is for previous one. Okay. For 2, we can't able to have the multiplicative inverse. Okay. If you go for 3, yes, 3 multiplicative inverse is 7, because if you go with 3 with 7, 3 into 7 is 21. 21 mod 10, you'll be getting as 1. So if you take in this example, we can able to have multiplicative inverse of 1, 3, 7 and 9 and more. Whereas the rest of the elements we can't have multiplicative inverse in z suffix 10. Right? They don't have inverse. So why sir they don't have inverse? And then the easy way to remember here in the sense, for example, if you're asking you find the multiplicative inverse of particular element in z suffix 10 or z suffix whatever the value of n, and if you find the GCD between this element and this element, okay, if GCD is not equal to 1, then obviously it won't have a multiplicative inverse. This is also other way to infer that whether the particular element have the multiplicative inverse or not. Right. So it means that it doesn't have a multiplicative inverse at all. Or you can also able to see, remember very easily in a shortcut manner. Okay, if you take this example, the previous example, right? Here the value of n is even number, right? All the even numbers here won't have. Actually, 5 is not an even number. 2, 4, 6, 8. Compulsorily, this 2, 4, 6, 8 won't have multiplicative inverse. Because if we take two even numbers and find the GCD, the highest or the greatest common divisor will be minimum will be at least 2. Right. How many of you got the point of multiplicative inverse? Actually, in trial and error method, it's difficult to find. We'll see easier way to find the multiplicative inverse. As of now, how many of you got the concept of this multiplicative inverse finding expression? That is, we take an element, you have to choose an element from that particular set, such that if you multiply those two elements and if you take a modulo operation, it should come to 1. Then we can able to call them as a multiplicative inverse to each other. If you people are clear with this concept, can you raise your hand? Yeah. Oh, we can go because here trial and error method you can go with small digits. Okay. How can able to find this multiplicative inverse? Since we can able to make use of our extended equivalent algorithm. Okay. So this extended equivalent algorithm can be used to find the multiplicative inverses here. For example, if you're going to find the multiplicative inverse of an element called B under a set of residues sets of its n, then you take the values of n and B, then you apply your extended equivalent algorithm. And if a GCD between these two is 1, then obviously you have the multiplicative inverse of B in this value. Okay. So generally in extended equivalent algorithm, we'll be finding the GCD, then the value of S, then the value of T. For finding the multiplicative inverse, we don't need the value of S here. Okay, we don't need the value of S here. So simply we will be finding the value of T, and this value of T will be the multiplicative inverse of that particular element. We will see an example. I hope everyone remembers extended equivalent algorithm. So in this case, if we take the value of n and b, initialize them for R1, R2, get the remainders and push it to find the GCD. And I hope you remember you'll be initializing the values of T1 and T2. T1 will be 0, T2 will be 1. Then T is nothing but T1 minus Q times T2, right? Then you'll be finding the value of T1 here, right? And this T1 will be the multiplicative inverse of this B. You'll see example here. They're asking you to find the multiplicative inverse of 11, okay, under a set of residues 26. So in this case, n is 26, B is 11. So I'll initialize this n to be my R1, 11 to be my R2, and I'm going to divide this 26 by 11. The quotient will be 2. 2 times 11 goes for 22. Remainder is 4. And t I'll be initializing 0 and 1. And this t is nothing but t1. T1 is 0 minus q times t2, which gives me minus 2. Right. And we are pushing this R2 to here, here, 1 is pushed here, minus 2 is pushed here. Second case, we are dividing 11 by 4. I'll be getting the quotient to be 2 because 2 times 8, remainder is 3. And in this case, it is T1 minus Q times, that is minus 2 times of minus 2. I'll be ending up plus 5. Right. Again, we are pushing and we are at last we are ending with a GCD of S1. And here the value of T1 is found to be minus 7. If we convert this minus 7 into positive 1, add the value of N, which is 26, minus 7 plus 26 gives me 19. Now if you multiply this 11 with 19 and if you take mod 26, okay, mod 26, you will be getting the answer as well. You can cross check this part. This is one way to find the multiplicative inverse using extended algorithm. That is, just take the value of t, and once you find the value of t, it will be acting as a multiplicative inverse of that particular element. You can able to see that both 11 and the multiplicative inverse 19 belong to this set of Z26. How many of you clear with this process? Kindly raise your hand. If you have any doubts, you can ask me. If you're clear with this process, kindly raise your hand. Clear? Can you tell me the answer for this one? I'll give you 5 minutes. I want you people to tell me the answer of 23 in Z suffix 100. So here your value of B is 23, value of N is 100. So this will be your R1, this will be your R2. I'll give you 5 minutes to post the answer in the chat box. If you face any difficulties or if you need any help while solving this one, kindly unmute yourself and ask. Use your extended algorithm and let me know the answer. Okay, Usha, you got 87. Okay, or minus 13. Okay, wait for some more answers. People are getting same 87 minus 23. Arun, just check whether minus 23 is correct or plus minus 13 plus 100 gives you 87, but minus 23 plus 100 gives you 77. Yeah, minus 13 more 100 gives you 87. Um, so, Venkat sir and Arun, just check whether you're getting minus 13 or minus 23. Many people are getting minus 23. You'll be getting minus 13 because if you inverse of 23, I mean, okay, what you people are saying is, okay, inverse of minus 23 is additive inverse actually, what you people are saying. Generally, compute minus 23 means it means additive inverse. Multiplicative inverse, you'll be getting as minus 13. Just check the flow here. Anyone have any doubt in this one? Just ask me. Yeah, someone to ask. Have people found where people have gone wrong? People who found minus 13, yeah, you're perfect. Minus 13 is the multiplicative inverse of 23 here. So if you go with a non-negative value, you'll be getting 87. You can just check multiply 23 with 87. Sorry, 87. And if you take mod 100, you'll be getting this one as 2001. Mod 100 will give you the value as 1. Is it clear, guys? Yeah, what's the ask? Okay.
No, sir, it was by mistake.
Okay. Because initially, first time people do make mistake, kindly practice these things, okay? So I hope you are clear with this part, right? If you're clear with finding a multiplicative inverse with the extended algorithm, can you raise a hand? Yes, Vijay Krishna, Venkat, Lahari, Govinda Lahari, yeah. Okay, I think then we will wrap up today's session with this one. It's already 6:45. We have like 2 or 3 more slides to complete this modular arithmetic. Okay, we will have the discussion next class before we move on to next topic. Okay, so with this, we'll wrap up today's session.